Galloping in a conductor is a very challenging situation for utility to manage. The reason for that is oftentimes a solution that's effective for one area may not work in a different area. But we have to go back and look at the fundamentals in terms of galloping. First off, I think the most important factor in the galloping situation is when the eyes are starting to form on the conductor, you wanted to know how much slack is in the conductor. A more slacky wire is more likely to gallop compared to a line that has less slack to it. It's a little bit tighter. What it means is they have less likely chance of galloping because the wires are not as loose. With TS Conductor, we have significantly lower somal sag, and when the eyes is forming, it's really driven by somal sag, not by eyes or wing. So you will have less slack to work with, and that is the most important factor in terms of analyzing galloping situation or propensity to gallop. The second part of the galloping, it really relates to how readily the conductor is going to rotate while the eyes is forming on the conductor. And why that is relevant. We normally look at eyes accumulating on the conductor, and you have wind blowing at the conductor, you have the tail side of the wing after it hits the conductor. So you will have an airfoil, which is eyes airfoil that are forming from the tail end. You want that to be strongly attached to the conductor in order to have galloping to take place. So then the question is, how do you get a very solid eyes layer and then the airfoil is strongly attached to it? There are some solutions in our industry in terms of anti-galloping. It's basically a dead weight that you clamp onto the conductor. It allows it to wobble, but it does not allow the conductor to flip. So you do not allow the conductor to flip, which means you cannot coat the conductor with eyes uniformly to build that solid eyes layer around the conductor. And then you have a strong tail, which is the airfoil shape. So if you have a conductor that has significant stiffness in terms of torsion, that's going to help you. TS Conductor features that encapsulated composite core. It is actually stiffer from a rotational perspective, and it's also got a much higher bending stiffness as well because of the encapsulated composite core. And both are beneficial. For the bending, for example, if the galloping is taking place, you're basically forcing the conductor to bend. It's going to require a much greater energy to start galloping motion. And to sustain that, it's also going to consume more energy to sustain that high magnitude motions. So again, the TS Conductor would be helpful with greater stiffness in the product design. And lastly, we use trapezoidal wire in the TS configuration typically. What it means with trapezoidal wire is the gaps between the aluminum strand are pretty small. Eyes will have a hard time to anchor into those interstitial gaps between the strand. So they will have a harder time to accumulate. And that will delay or make it hard for the galloping motions to start. And there is the industry perception at some areas that, okay, trap wire is bad. That is not necessarily the most accurate statement, because what they're referring to is most likely ACSS conductor with trapezoidal configuration. And these conductor, they have significant weight in the ACSS with trapezoidal wire. They also have a lot of somal sag. So when you combine these together, you have tremendous slack in the wire to begin with. When we say that the trap wire, in those situations, they are more prone to gallop, It was because those conductors have significant slack in the wire when the ice is forming. That's why it is bad in terms of galloping situations. And TS conductor doesn't have that slack issue. So it will be able to manage the gallopings in a significantly better way. So these are the reasons why TS conductor should do as good as you could have hoped from a conductor design perspective.